So we've looked at polar bonds, but now we are going to look at molecules as a whole. In the first molecule, Cl2, okay, there is only one bond. It's a chlorine-chlorine bond. This bond is non-polar. Both of the atoms are the same. Therefore, neither chlorine atom has a greater pull on the electrons, and the electrons are evenly shared. We say it's non-polar. In the next example, I've got 4 bonds. I've got 4 carbon-hydrogen bonds. Each of these bonds is non-polar. Okay, there's a slight difference in electronegativity between carbon and hydrogen, but not enough for either atom to have a greater share of the electrons. And I say that each of these bonds is non-polar. You've got 4 bonds, they're all non-polar. Overall, the molecule is going to be non-polar. The next molecule, okay, I've got more bonds. I've got a carbon-carbon bond. So this bond exists between 2 of the same atoms. If they're both the same atoms, the bond is not going to be polar. The other bonds you've got are carbon-hydrogen bonds. You've got 6 carbon-hydrogen bonds in total, but they're all carbon-hydrogen bonds, okay? We've seen already that a carbon-hydrogen bond is non-polar. The carbon-carbon bond is non-polar. So overall, the molecule is going to be non-polar. Okay, for something to be polar overall, it must have at least one polar bond. I'm going to write that down here in my bottom corner. Okay, I'm going to write criteria for a polar molecule. Criteria. Okay, for a molecule to be polar overall, it must have at least one polar bond. If all bonds in the molecule are non-polar, then the molecule itself will be non-polar. Okay, so let's look at something else that does actually have polar bonds in it. Okay, I am going to draw carbon, and this time I'm going to draw it bonded to 4 chlorines instead of 4 hydrogens like I did above. Okay, chlorine is more electronegative than carbon. If you look at the pulling values, okay, chlorine has a greater pull on the electrons. So in each of these carbon-chlorine bonds, the electrons are going to sit closer to chlorine. That's going to make chlorine delta negative in every case. And you're going to have a delta positive carbon. Okay, remember it's delta positive because carbon's not actually losing an electron. So it doesn't have a full positive charge, it has a partial positive charge. And similarly, chlorine's not actually gaining the electron, it's just partially gaining it. So we say it's delta negative, not fully negative. Okay, so I've got 4 polar bonds in this molecule. You might then assume that overall the molecule is polar. Okay, but in order for a molecule to be polar, there has to be a clear separation of charge within the molecule. There has to be one negative end of the molecule and one positive end of the molecule. A clear separation of positive from negative. In CCl4, okay, you have got negative chlorines the whole way around the outside, and then you've got a positive center, okay? You don't just have one negative and one positive end. The entire outside is all negative. There's not that clear separation across the molecule of one side being positive and one side being negative. So even though you've got 4 different polar bonds, the molecule itself is actually non-polar. And we say the reason it's non-polar is because you have got symmetry within the molecule. And because you've got symmetry, all of those dipoles, and remember, dipoles is just that separation of charge across a covalent bond, so the delta positive, delta negative, all of those dipoles effectively just cancel each other out. Okay, because you've got symmetry. If I look at another example, I'm going to look at CO2, which is carbon double bonded to oxygen on each side, okay? Again, carbon, oxygen, carbon is going to be delta positive, oxygen is going to be delta negative. And again, in this situation, although you've got 2 polar bonds, you don't have a positive end and a negative end. You've got 2 negative ends. So again, what's going to happen is that these dipoles are just going to cancel each other out. And they're cancelling each other out because you've got symmetry in the molecule. So you've got 2 bonds that are exactly the same, pointing in opposite directions. That gives you symmetry. So again, this is going to be non-polar. And it's non-polar because you have got symmetry. And any molecule that you've got symmetry those dipoles are just going to cancel out. Okay, now symmetry can sometimes be difficult to spot, okay, especially over here when they're like 3D molecules. It can be difficult to see if a molecule is symmetrical or not, okay. If you have symmetry, the dipoles will always cancel out, but symmetry is not always easy to spot. So we're going to have a look at an easy way to spot if a molecule is symmetrical or not, okay. In order for something to be symmetrical, the bonds have to be the same. So in the above examples, I had 4 bonds. They were all carbon-chlorine bonds. All of the bonds are the same. In this example, I've got 2 bonds. They're both carbon, double bond oxygen. The bonds are the same. Okay, so to have symmetry, those bonds all have to be the same. Okay, and they have to have a symmetrical shape. Now, we've looked in previous videos at the different shapes that molecules take on. Some molecular shapes are symmetrical, and the shapes that are symmetrical are as follow. If all of the bonds are the same, and the molecule is trigonal-planar, it's going to be symmetrical. If all the bonds are the same and the molecule is tetrahedral, it's going to be symmetrical. If all of the bonds are the same and the molecule is linear, it's going to be symmetrical. If all the bonds are the same and the molecule is octahedral, it's going to be symmetrical. Okay, in the above example, all my bonds are the same and it's tetrahedral, therefore it's symmetrical. Symmetrical, the dipoles cancel out and it's non-polar. In the second example, all my bonds are the same and it's linear. If it's linear with the same bonds, it's symmetrical, the dipoles cancel out and it's going to be non-polar. Okay, so if I come back down here to my criteria for a polar molecule, you need to have no symmetry, because if you've got symmetry, those dipoles are just going to cancel out. Okay, we're going to look at another example. All right, I'm going to draw this over here, and I'm going to draw something very similar to what I've drawn already, but I'm going to replace one of those chlorines with a hydrogen. Okay, I've got a tetrahedral molecule, okay, and I've got polar bonds in there. I need to see if it's symmetrical or not. In order for something to be symmetrical, all bonds have to be the same. In this molecule, are all bonds the same? No, the bonds are not all the same. So even though it's still tetrahedral, which is a symmetrical shape, because the bonds are not all the same, this is now a polar molecule. Okay, so you have your polar bonds, you now have a not symmetrical molecule, it makes it polar molecule. If I looked at another example, okay, so if I drew this, okay, so SO2, so sulfur is more electronegative than, oxygen is more electronegative than sulfur, so I've got delta negative and I've got delta positive, okay. First glance, this looks exactly the same as what I have before. You would say you've got symmetry and that these dipoles are going to cancel out. But what shape is SO2? Okay, CO2 is linear. What shape is SO2? Okay, what I haven't drawn in here is the lone pair on sulfur. Remember, carbon has only 4 electrons. 1, 2, 3, 4 are all involved in bonds with oxygen. Sulfur has a lone pair of electrons that are not involved in bonding. And because it's got a lone pair, the shape of this molecule is going to be bent. It's going to be non-linear. Bent is not one of my symmetrical shapes. So even though my bonds are the same, I do not have a symmetrical shape. That means unsymmetrical or asymmetrical. I'm going to call it unsymmetrical. And the dipoles do not cancel. Dipoles do not cancel, and overall my molecule is polar. Okay, it looks very similar to above, but when I look at the shape, it's bent. It's not one of my symmetrical shapes. Dipoles will not cancel, and it's going to be polar. Okay, if I do another example, I'm going to do NH3. Okay, and I remember my lone pair. Okay, do I have polar bonds? Yes. Nitrogen is more electronegative than hydrogen, so all of those bonds are going to be polar. So I do have polar bonds. Now I need to ask myself, do I have symmetry? Are all of my bonds the same? Yes. Is NH3 one of the following shapes? NH3 has 3 bond pairs and it's got 1 lone pair. This makes it trigonal pyramidal. Is trigonal pyramidal one of my symmetrical shapes? No, it is not. So although all of my bonds are the same, it's not a symmetrical shape. That means the dipoles do not cancel. And overall, it is going to be polar. I have got no symmetry. It's going to be polar. Okay, so it's really, really important that you can work out the shapes of the molecules. It mightn't be immediately obvious when you draw it if you've got symmetry or not. But if you know the actual shape, you just need to know which shapes are symmetrical, which shapes are not symmetrical. So trigonal planar, not symmetrical. Bent or nonlinear, not symmetrical. So if it's either of these two shapes, it doesn't matter if the bonds are the same, the dipoles are not going to cancel. If it's one of these shapes and the bonds are the same, the dipoles will cancel. Look at another example. We'll look at water, H2O, okay? So do I have polar bonds? Yes, I do, okay? Oxygen's more electronegative than hydrogen, so I have polar bonds. Do I have symmetry? So are both of those bonds the same? Yes, both of those bonds are the same. Is water one of these 4 shapes? No, okay? Oxygen has got 2 bond pairs and 2 lone pairs, meaning its shape is bent or non-linear. That is not one of my symmetrical shapes. So even though my bonds are the same, in a non-symmetrical shape, the dipoles will not cancel, and this will end up being a polar molecule. Okay, I'm just going to do one more. If I look at BCl3, so I've got boron bonded to 3 chlorines. Okay, do I have polar bonds? Yes. Chlorine is more electronegative than boron. You're going to have polar bonds. Are all of these bonds the same? Yes, they are all the same. So I've got 3 polar bonds. They're all the same. Is BCl3 one of the symmetrical shapes? In boron, you've got 3 bond pairs. Boron's in group 3. It's only got 3 electrons. They're all involved in bonding, so there are no more electrons. So I've got 3 bond pairs, no lone pairs. That makes boron trigonal planar. Is trigonal planar one of my symmetrical shapes? Yes, it is. Okay, so all of my bonds are the same. It's trigonal planar. That means I do have symmetry. That means my dipoles will cancel out, and that means it is going to be non-polar. Okay, so in your questions, in exercise 2, in the next video, I'm going to go through the answers to exercise 2 on page 18. I'm just going to go through the answers to question 6. So I'm going to start by going through all of these answers. All of these answers to question 6 in exercise 2 on page 18. And then after going through those, I'm going to go through the exam questions. So if you have a go at exercise 2 on page 6, on page what? No, not on page 6. Exercise 2 on page 18, question number 6. Have a go at those questions first, then do the exam questions, and then tune into the next video for all of the answers.